Hello everyone. In the previous part of this lecture, we discussed the radioactive decay chain and also derived the expression for the activity of a daughter isotope, which is also radioactive. And based on that equation, in fact, we generalized that equation for multiple decays to find out the activity of granddaughters. We also discussed that if the parent is short-lived compared to the daughter isotope, then this is a case of no equilibrium. After the parent activity has decayed down, the daughter isotope decays with its own half-life. Now I will discuss a different situation where the parent is long-lived than the daughter isotope, and that is where we will call it as a radioactive equilibrium. So this is the case of a parent being long-lived than daughter isotope, and there are two cases of this type here. In the first case, the parent is roughly 10 times half-life, having 10 times more half-life than the daughter isotope, and there is another case where the parent is much longer lived, maybe 100 times or even more than that. So we will discuss these two cases separately, and they have slightly different implications, that's all. So let us take the case of this 10 times more parent half-life than daughter, and I have given an example here. 140 barium having a half-life of 12.8 days decays to lanthanum 140 having half-life of, let us say, 1.6 days, so roughly 10 times the parent. It is not very hard and fast that it has to be 10 times. It could be 9 times, 8 times or 12 times, no? So, but just order of that. And why it is so, I will explain very soon. And it is decaying to 140 cerium, which is stable. So let us see in mathematically what happens and then see graphically what happens. So when we have a large time elapsed, the time elapsed, so again here I will put the equation here, activity of daughter equal to activity of parent, lambda 2 upon lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2 t. This is the general equation for the activity of the daughter product, here lanthanum 140 as a function of time. So what we are discussing here, that when the time, so here lambda 1 is smaller than lambda 2. So when the time elapsed is much more compared to the half-life of the daughter. The daughter is short-lived. So after several half-lives of the daughter, this term e raised to minus lambda 2, because lambda 2 is very high. So e raised to lambda 2 term tends to 0. When this term tends to 0, you can see here activity of daughter A2 equal to A10 lambda 2 upon lambda 2 minus lambda 1 e raised to minus lambda 1 t. You see here what is happening now. This is the decay of parent, whereas we are seeing the change in the activity of daughter. So daughter isotope is decaying with the half-life of parent after a sufficiently long time. That means several half-lives of daughter. So after several half-lives of daughter, the daughter activity starts decaying with the half-life of parent. So even after several half-lives, because the daughter activity is being fed from the parent, the daughter activity is there, but it is decaying with the half-life of parent. So as a result of that, the daughter activity reaches a maximum and then decays with the half-life of parent. So that means this is like a transient. That is why it is called a transient equilibrium. For a moment, the daughter activity reaches the maximum and then starts decaying with the half-life of parent. So I have tried to explain this in this graph, which is again in the linear scale. We are plotting A, not log A, as a function of time. And so the activity of parent The parent is long lived. The parent is decaying in this way, and the daughter activity starts going from zero because initially there is no daughter activity, reaches more than that of parent. Now you see the implication of this term in this equation. This term lambda 2 upon lambda 2 minus lambda 1 will be more than 1. So at that case you will see A2 will become, so you can write this as A1 lambda 2 upon lambda 2 minus lambda 1. A1 means A1 0 e raised to minus lambda 1 t, and so A2 will be more than A2. A2 will be more than A1, and this is the condition which is meaning by this equation. So the activity of daughter becomes more than that of parent, and again after some time starts decaying with the half-life of parent. So that is what we call as the transient equilibrium. Okay, so now let us do an exercise of resolving the total activity into that of the parent and daughter in the case of a transient equilibrium. So when we have a freshly purified parent isotope, then the total activity of this sample, if we have a freshly purified, the total activity will increase and then subsequently decrease in this fashion. Here I am plotting total activity in the logarithmic scale as a function of time, and from this data let us try to find out the half-life of parent and that of the daughter, and also their initial activity we can find out. So as you know, the total activity can be given as the parent activity, that is A10 e raised to minus lambda 1 t, plus the daughter activity A10 lambda factor e raised to minus lambda 1 t minus e raised to minus lambda 2 t. So now what happens that when that lambda 2 is become quite large, because that lambda 2 means the decay constant of daughter, that is higher than lambda 1, then this exponential term, this term tends to 0, and therefore the total activity becomes parent activity plus daughter activity, and both of them following the half-life of parent. So you can see here the parent activity at a later time is in logarithmic scale, it's straight lines. That means it is exponentially decaying, and it should be the decay constant of parent. So this is the data which represents the half-life of parent. So you can extrapolate this to 0 time and draw a line parallel to this line. This is the decay of the parent in the total activity. And so from here we can find out the half-life of parent. Now the excess activity from here to here is due to the growth of the daughter. So if you subtract point by point from here, then you will get the growth of the daughter, which will grow, become more than the parent activity, and then again decay with the half-life of parent. So this is the growth of daughter activity. And if we had not done the separation of daughter from parent, then if you can extrapolate this to 0 time, that gives you activity of daughter which was present in the sample before the separation was done. So this was the activity of daughter which was in the sample, and this is the activity which is growing in the sample. For the subtraction of this to this data will give you the daughter decay. The daughter which had been separated from the parent as a result of the radiochemical separation, which is now kept separately, will be decaying with its own half-life. And so from the decay data we can find out the lambda and hence the half-life of daughter. So this is how you can resolve the parent total activity into that of the parent and the daughter. You can find out their half-lives and you can find out their initial activities. This was the exercise that I thought it should better to do it for the transient equilibrium. Similarly, you can do for the settled equilibrium. Now we discuss the situation that the daughter activity grows, reaches a maximum and then starts decaying with the half-life of parent. So what is the time to reach the maximum daughter activity? Let us discuss this in this slide. The activity of daughter changes with time using this expression A10 lambda factor into e raised to minus lambda 1 t minus e raised to minus lambda 2 t. So the time at which the activity of daughter activity atoms become maximum, then the derivative of A2 will be 0. So let us differentiate this A2 as a function of time and equate this equal to 0 to get the time. So when this expression is equal to 0, t becomes Tm, this may maximum time. So this you can say if you put this other constant terms as k, like A10 lambda factors will be constant. So we have differential of this minus lambda 1 e raised to minus lambda 1 Tm plus lambda 2. So minus will become plus e raised to minus lambda 2 Tm equal to 0. So this equation boils down to lambda 2 e raised to minus lambda 2 Tm equal to lambda 1 e raised to minus lambda 1 Tm. So you can now try to separate the time factor. So you bring the lambda 1, lambda 2 this side, it becomes e raised to lambda 2 Tm minus lambda 1 Tm equal to lambda 2 by lambda 1. And now you can arrange them. Ln lambda 2 by lambda 1 equal to Tm, take out lambda 2 minus lambda 1. So Tm, the time to reach maximum daughter activity, equal to ln of lambda 2 by lambda 1 upon lambda 2 minus lambda 1. So essentially you have here Pm equal to ln lambda 2 by lambda 1 upon lambda 2 minus lambda 1. Using this expression, you can try to find out, and if you want to put this ln in terms of the logarithmic, you can put 2.303 log base 10 lambda 2 by lambda 1 upon lambda 2 minus lambda 1. So using this formula, you can calculate the time when the daughter activity will reach maximum in a case of a transient equilibrium. If for that matter, even in the case of a no equilibrium case, the daughter activity will reach a maximum, and you can calculate at what point of time it will happen. Okay, now I will come to the second case of equilibrium, and that is called as the secular equilibrium, where the parent is much longer lived than daughter, roughly of the order of 100. So it is not a very hard and fast, it has to be exactly 100 times, but of the order of, it could be even few hundreds or even thousands also. So, but it is more than, let us say, typically more than 100 or more than that. And one example I have given here, strontium 90 undergoes beta minus decay to yttrium 90, which also undergoes beta minus decay to zirconium 90. The half-lives 28 years, 64 hours, so let us say typically less than 3 days, 2.64 days, and zirconium 90 is stable. So again use the assumptions that at very large time compared to the half-life of the daughter, e raised to minus lambda 2 term become 10 to 0, because lambda 2 into t will become very large positive number. So exponential of a very large negative of a large negative positive number will become 0. So A2 equal to A10 lambda 2 upon lambda 2 minus lambda 1 e raised to minus lambda 1 t. Now compare this with the secular equilibrium and transient equilibrium case. Here lambda 2 is much larger than lambda 1 because T1 is much larger than T2. And so in such a case you can neglect lambda 1 with respect to lambda 2. So in the denominator, this term lambda 2 by minus lambda 1 will become lambda 2, and so this will get cancelled out. So because of this approximation, this term vanishes, it becomes 1, and so what happens to this term? A2 equal to A10 e raised to minus lambda 1 t, and this term is nothing but activity of parent. So you can see here the very meaning of secular means they are same. In the case of transient equilibrium, the daughter activity is decaying with the half-life of parent, but it is not same. In fact, it is more than the parent activity because of the lambda factors. In the case of secular equilibrium, once the equilibrium is established, the activity of daughter and parent becomes same, A2 equal to A1. This I have tried to illustrate using this graph here. The activity, now see, though it is linear scale, I have put the graph as a linear, the activity, that means during the period of our observation, the activity is not changing, the parent activity is not changing, and so A1 is becoming flat. But the daughter activity will start growing and finally will become equal to that of the parent activity. So this is the difference between the case of the secular and transient equilibrium. In transient equilibrium, the parent is not that long-lived that it will not decay with time. Parent is also decaying, but the daughter grows and becomes more than that of parent activity and then starts decaying with the half-life of parent. Now I will give you an example of this secular equilibrium here, and here now I have taken this as a log scale because the growth of the daughter is looking like a linear, that means the activity is plotted in the linear scale, a logarithmic scale. So again, this is the experiment one can do in the laboratory to resolve the total activity into parent and daughter activity and then find out their half-lives. So suppose you take a parent isotope and you do a chemistry to separate it, purify it. You have pure, freshly purified parent activity, then it will, total activity will grow like this. Okay. And then you extrapolate to 0 time. So there may be time here. So extrapolate 0 time. This is the 0 time. Now in secular equilibrium, so the parent is very long lived. So you can draw, this is the decay of parent. You can draw a parallel line to this. This will represent from this point. This will represent the parent decay. So these two lines, you know, this is the decay of a freshly purified parent isotope, and this is the decay of activity, total activity, if you did not purify the parent. So when you did not purify the parent, activity was here. That is the total activity of parent plus daughter, and they are in equilibrium. Once we separate, then there is no daughter activity becomes 0, and it starts growing in the parent total isotope. So this you can find out from, again, this separation. These points you separate, you subtract this data from this data. This is the total activity. This is the without separation, and with separation, if you subtract, then you will get this data that is representing the daughter activity. Is it like, you know, if you do a separation of daughter activity, put it in a separate flask, then there it is not growing from parent, it will decay in its own half-life, and that is what is represented by this graph. So from this graph we can find out the half-life of daughter and the total activity. The total activity, the activity of daughter is nothing but the same as that of parent because they are in the secular equilibrium. So that is why the parent activity is here, it will become double after equilibrium is established. Now you can see here, this is the total activity, this is total activity at equilibrium, and this is the parent activity. So this, because of the logarithmic scale, this is equal to this. That is what I wanted to convey, that in logarithmic scale it is such that like 1 to 2 and 2 to 4 are there is a different scale in the log scale. And the typical example I have seen, I have shown here, the experiment in fact is done in the laboratories. You take 137 cesium having half-life of 30 years, and it undergoes beta minus to the isomeric state of 137 barium, which has a half-life of 2.54 minutes and which emits a gamma ray of 661 keV to 137 barium ground state, which is stable So in the laboratory experiments, the cesium-137 is held in a column which is selectively taking up cesium, and then when you elute the barium, you take some solution, sodium chloride solution, barium-137 will be eluted, or cesium will not be eluted. And so whatever barium is eluted, it will decay with the half-life of 2.54 minutes, because it is not growing now. It is in a separate test tube, and so you can get this data only from the separated barium-137. And after again, sometime it will again grow, like the time to reach the maximum activity will be typically 4 times the daughter half-life. So you can do this experiment multiple times from a column which is containing the 137 cesium, and that like for years together you can use the same column. So this is a experiment in the laboratory for radiochemical separations. Now I will just discuss why I took so much time to discuss these equilibrium cases, because they have lot of applications. So the applications of radioactive equilibrium in particularly nuclear medicine, or even if you want to use an isotope frequently, then if you have a parent which is long lived, you can make a generator. So radioisotope generators, the radioisotope generators are based on the radioactive equilibrium. So I will give you 2 examples, one of transient equilibrium and one of secular equilibrium. This is the case of technetium-99M generator. Technetium-99M is called as the workhorse of nuclear medicine. It is used in diagnosis of the diseases in the body. So it is actually having a half-life of 6 hours. So you cannot you produce this isotope, take to the hospitals, and then you have to keep on supplying every day the technetium-99 activity. But if you have a generator system, you have a parent which is long lived, like 99 molybdenum, 66 hours half-life, and it is decaying by beta minus to 99M technetium, which undergoes internal transition to gamma ray decay to 99G technetium, having half-life of 10 to the 5 years. So now let us see, you calculate the time when the activity of technetium-99 will reach a maximum. Using this formula, just now we derived this formula, the time taken for 99M technetium to reach its maximum is 32.8 hours. So the technetium-99 activity will grow in the sample, reach a maximum, and you can then separate technetium-99M, use it for the investigation, diagnosis like SPECT analysis, and then after one day, 22.8 hours, again you have same amount of technetium in the column. So this is what is the concept of a radioisotope generator. So here on the left hand side, I try to plot the activity of molybdenum. So this is the activity of molybdenum, which is decaying exponentially. It is a linear scale, and now the technetium activity grows in the let us say typically one day it reaches this value, and then you elute this technetium-99 from that column. Molybdenum remains in the column, and this activity now you can use in the hospitals for diagnostic purposes. Next day again you elute technetium-99. Now the molybdenum is decaying, so this activity also will be less. You again elute technetium-99 next day morning, carry out the test that day. Third day you again do the separation, 4th day and 5th day, and so on. So normally Monday the hospitals are supplied with molybdenum-99, and for that week, because this half-life is 66 hours, 2.6 days or so, so you can carry on this tests for the whole week, and next week again you have fresh lot of molybdenum-99. Now I have put a question mark here. Why does the technetium-99M activity do not exceed that of 99 molybdenum? I explained that in the transient equilibrium, daughter activity will be more than that of the parent. So it should have actually gone up and more than molybdenum. But in this particular case, what happens? You are measuring the gamma ray from the technetium-99 sample, and the gamma ray have certain abundance. For 100 decay, this gamma is emitted only 87 times. So this is called abundance percentage, 87%. So this is not the complete decay of the 99 technetium. Only the 87% of the time technetium-99 decaying, this gamma ray is emitted, and that is why the gamma ray activity becomes less than the parent activity. Instead of going more than molybdenum, it is becoming less. And so this is a typical case of a transient equilibrium where you can use generators based on this concept for the applications in healthcare. Now, another application of this generator is the 90 strontium, and this is the case of a secular equilibrium where the parent is much long lived than daughter. So you see here that strontium 90 is having half-life of 28 years, undergoing beta minus decay to yttrium 90 having half-life 64 years, and this is undergoing beta minus decay to 90 zirconium, which is stable. So now this is a case of secular equilibrium because the parent is much long lived than that of the daughter. The ratio of half-life is more than 100, even is quite high. So what I have plotted here is the activity of a case where activity of the strontium 90 will not change with time. So the half-life is 28 years. You are measuring for a day or two or few days. There will be no change. But the activity of yttrium 90 will grow. So it was, let us say it was 2.6 days. For about 10 days, 3-4 half-lives, the activity of yttrium 90 will grow, and then it will become flat. It will become equal to that of the parent. So at this point of time, yttrium 90 can be separated, and again it will start growing, and you reach the maximum value. So here both strontium 90 and yttrium 90 are pure beta emitters. That means the activity of the daughter will be equal to parent. There is nothing like a gamma ray abundance factor coming into picture here. And also every time over a period of even say few months, the activity of daughter will again become equal to that of parent. So you can use this generator to separate 90 yttrium, which is also another important isotope useful in therapeutic applications. Yttrium 90 is used in many therapeutic applications in nuclear medicine. So this is the case of secular equilibrium where you have yttrium 90 generators. Now lastly, I come to the case of a new rate of reaction in production of radioisotopes. We have just seen molybdenum 99 or strontium 90. So they are also produced in some process like fission or in a nuclear reaction. So the decay growth of activity produced in a nuclear reaction also follows similar pattern as we discussed in the radioactive decay chain previously. So here I give you an example of a nuclear reaction. Sodium 23 captures a neutron, becomes sodium 24, and which emits a gamma ray. The prompt gamma is emitted, and we have the 24 sodium in ground state undergoing beta minus decay to magnesium 24, which is stable. So what we are essentially seeing how the activity of sodium 24 will change with time when it is produced by N-gamma reaction on sodium 23. So this is analogous to A going to B by nuclear reaction and B going to C, that C is magnesium 24. So instead of A going to B by beta minus decay or alpha decay, here we have A going to B by N-gamma reaction. So the profile will be similar. So here we can set up the equation for the formation of B, dNB by dt equal to R. This is the rate of reaction minus dNb lambda b, and you can again solve the same way, that is dNb by dt plus nb lambda b equal to r. And if you recall the integration factor, e raised to lambda bt, e raised to lambda bt. If you integrate, what you will be getting is nb lambda b equal to r 1 minus e raised to minus lambda b t. So the activity of daughter, those steps I have not shown because they are similar to what we showed earlier for the case of A going to B going to C. And so here this activity, this is called actually the saturation factor. That means the activity of B will grow by this factor 1 minus e raised to minus lambda t. And what I have shown here is the same thing as a function of time. This factor, saturation factor, this is the rate of the reaction. So saturation factor will grow in this fashion and become equal to 1 after some 4-5 half-lives. So this, in fact, this graph is used to decide for how much time we need to irradiate this particular target in the reactor or accelerator. So suppose you have 1 half-life, then 50% is produced. To get 100%, you get about 4 half-lives. More than that, there is no gain. So this is an idea to fix the time of irradiation, and the same profile you get for the activity of daughter activity when you are producing it in the irradiation. So that's all I have to say, and in the next lecture now I will talk about nuclear structure and stability. Thank you very much.